Last time we looked at the relationship between pressure and volume of a gas, and we learned that through Boyle's law, as one of these increases, the other one decreases. It is an inverse relationship. So for example, if pressure increases, volume will decrease. Today we're going to take a look at Charles' law, and Charles' law looks at the relationship between volume and temperature of a gas. And this is a direct relationship. So basically with this then, the volume of a gas increases proportionately with temperature. And just like Boyle's law, there are things that have to stay constant. So in this case, it's pressure and amount is kept constant. So for this, the pressure has to stay constant and the amount or moles of gas has to stay constant as well. So again, just like we did with Boyle's law, we're going to take a look at this graphically and we're going to take a look at it mathematically. We're going to derive the equation. Again, you are not required to know how to derive these equations. It's just to kind of show you how observations in a lab can lead to actual mathematical formulas. So this is a direct relationship. So V is going to be directly proportional to T this time around. Now, to, again, make this an equation, we add a variable, okay, a constant. And this is going to be, we're going to add K again. So V equals K times T. And now I'm going to solve for K. So that becomes K equals V over T. And just like in Boyle's law, K equals V1 over T1. So that value of that constant is going to be the same, whether I've got it one condition or two, sorry, that should be a two, or a second condition. And so I can put them both together. So V1 over T1 equals V2 over T2, and that's going to be Charles' law. Now again, pressure stays constant and moles of gas stays constant. So you can see that again, we've got this ratio situation where we're comparing our first condition with the gas and then finding out some unknown condition of the second. Now, the next thing we're going to do is we're going to graph it. And of course, it is a linear relationship. So you can see here, we've got several gases that are graphed. So we've got helium, methane, water, hydrogen, and dinitrogen oxide. And you can see here that I get these straight lines. Now, if you extrapolate, which means basically sending it back down to where it crosses, okay, the x-axis, they all meet in a particular temperature. And this is an important temperature. This is basically called absolute zero, and it's minus 273. We're going to use 0.15, not 0.2. We're going to use one more decimal place in our calculations, degrees Celsius. And that is believed to be the temperature where molecular motion stops. So this leads to a different temperature, basically unit that we use, and it's called the Kelvin. And Kelvin is really important for gases because it's not based on, for example, degrees Celsius, it's based on water, where 0 was set where water freezes, 100 was set when water boils. This is actually based on molecular motion. And because really that's what we're measuring with temperature, that's a much more accurate temperature scale than degrees Celsius. So again, we're extrapolating all the way down. So this temperature is called absolute zero. And you've probably heard of that before. And this is the minimum temperature that can be attained. And so the temperature scale that we use is the Kelvin temperature scale. And so to convert from one to the other, what we do is we just add 273.15 to the degrees Celsius temperature, or subtract 273.15 from the Kelvin if we want to go back to degrees Celsius. Now, this is very important for you guys to know. When you're using Charles' law, you must use Kelvin. I cannot state this enough. So when using Charles' law, you must use Kelvin. Because again, Kelvin represents molecular motion, not a comparison of one temperature to another. So it's very important that you use Kelvin. So our example here, and you can see that it's very straightforward. So this is 20 degrees Celsius. We're going to add 273.15 Kelvin. Oh, sorry, just 273.15. There's no Kelvin or anything. It's just the conversion factor. And so this becomes 293.15 Kelvin. Now, if I were using this in a calculation, then this would be where I would keep these number of significant digits. But in this question, because the answer is the temperature, I need to make sure that I round to the lowest number of significant digits. So rounded correctly, this would be 293.2 Kelvin, okay? And again, I wouldn't round it. If it was just an intermediate step, I was using it with a formula, but to change it to Kelvin, I do have to round it to the correct number of significant digits. So again, we're going to use kinetic molecular theory, or KMT, to explain what's happening. So as temperature increases, what's going to happen is that the particles are going to move faster. So their average kinetic energy is going to be faster. And so what happens is the volume of a gas will increase. It can go further. It has more collisions. It can increase the volume of a container if the volume of a container can be changed. All right, so let's do some practice questions here. And again, you're going to see that this is very similar to Boyle, so we'll just do a couple of practice questions. And it says 1 mole of gas occupies a volume of 22.4 liters at STP. So again, I know that I have this volume at this particular temperature. And then it says what volume will it occupy at 500 degrees Celsius. So I need to find its volume at 50 degrees Celsius, not 500. All right, so here we go. So I know that my V1 is 22.4 liters. Temperature 1, I need to figure out what my temperature is at STP. And if you look in your data booklet, it is either 0 degrees Celsius, or I think in your data booklet we wrote it as Kelvin. So it's basically 273.15 Kelvin. So 0 plus 273.15 is 273.15. Now, I've got my second temperature, which is 50 degrees Celsius. And what I like to do is I like to change it into Kelvin here, because I don't want to forget while I'm doing the calculation later on. So I just add 273.15 right there. I don't forget to do that later on. And then I'm looking for my volume. And again, remember, your temperature has to be in Kelvin. So unlike the flexibility with pressure units, as long as they are both the same, here they have to be Kelvin. All right, so I write down Charles' law. So V1 T1 equals V2 T2. I am looking for V2, so I multiply both sides by T2. So rearranged, this is T2 V1 over T1 equals V2. Okay, I'm going to substitute in. So I have 323 Kelvin, 0.15 Kelvin, times, and this is going to be 22.4 liters, and I'm dividing by 273.15 Kelvin. My Kelvin units cancel out. I'm left with liters. And because my temperature increases, I expect my volume to increase as well. And I get an answer of 26.500 ... liters. And to 3 significant digits, this becomes 26.5 liters, and you can see that our volume did actually increase. All right, so I'm hoping that you see that these calculations are as straightforward as Boyle's law. However, there is one thing that I want to show you guys with the second one, and it is when you are solving for temperature. Because temperature is in the denominator, I need to make sure that I bring that unknown up into my numerator. So let's read through the question and I'll explain a little bit better. It says, an industrial gas storage tank with an adjustable pressure has a volume of 100 liters. So again, my volume is going to be 100 liters. When the gas temperature is 55 degrees Celsius, and it wants me to calculate the temperature of the gas when the volume drops to 75 liters with no loss in pressure. Okay, so V1, this is going to be 100 liters. T1 is 55 degrees Celsius. I'm going to change it to Kelvin right away. So 328.15 Kelvin. And V2 is 75 liters. And I'm looking for T2. All right, so again, getting back to what I was saying about temperature and its need to be in the numerator. So V1 T1 equals V2 T2. So I'm looking for T2. Do you guys see that it's in the denominator, not the numerator? I need to bring it up into the numerator to solve it. Otherwise, I'm solving for 1 over the temperature. So there are ways of rearranging this. I can multiply both sides by T2 to bring it up into the numerator and then rearrange the formula. But there's a much easier way to do this. And all I do is I flip the formula around. So T1 over V1 is the same as, and T equals T2 over V2 is the same as the flipped version. It means the same thing. They are the same thing. So now you can see that my temperature is in the numerator. So now I can multiply both sides by V2. And this gives me T2 is equal to V2 T1 over V1. So I substitute in. V2 is 75 liters. T1 is 100 liters. And I divide, oh, sorry, I did something there. T1 shouldn't be liters. Okay. T1 is 328.15 Kelvin. And V1 is now 100 liters. So we've dropped the volume, so our temperature should drop as well. My liters cancel out. And this turns out to be 246.1125 Kelvin. Now, it doesn't tell us to change it back to degrees Celsius, so we would just round it to the correct number of significant digits in Kelvin. You don't change it to degrees Celsius unless it asks you to or unless you want to. So this would be 2.5 times 10 to the 2 Kelvin. I am just going to switch it to degrees Celsius to show you. But again, this question doesn't ask for it, so you don't have to actually do this. So this would be 246.1125 Kelvin minus 273.15. This changes it then to degrees Celsius, and this is minus 27 degrees Celsius, okay? But again, no need to change it into that because the question did not ask for that. So I hope that this made sense. And remember, very important, and I know I keep on repeating it, but I still always have students who forget, you need to change your temperature to Kelvin in order for this to work. Kelvin is measuring molecular motion of of the gas particles. Degrees Celsius is not. So please make sure that you change that in order for this to be accurate, and everything should go relatively well.